Good afternoon, everybody. My name is Edgar de los Santos. If you can hear me, can you please press the button with the hand? Alright, thank you so much. I am part of the technical support team here at Midas, and today we're gonna talk about dynamic analysis using Midas Civil. We're gonna go over a little introduction on seismic analysis, and then we're gonna go over the eigenvalue analysis, response spectrum analysis, pushover analysis, time history analysis, and we're gonna go over its application in the program as well. Going into the seismic analysis itself, seismic analysis is a part of the structural analysis and the calculation of the response of a structure to an earthquake. It is part of the structural design process of a bridge in this case, or any other structure. It's also part of the seismic and engineering, and also the structural evaluation and retrofit in seismic zones. For existing bridges, these types of analysis are also performed to see or to determine what would happen if there is a earthquake of certain event, seismic event. Why is it important? It is important because it allows us to visualize the response of a bridge or a structure during the earthquake, which allows us to obtain the additional forces or deformations that would generate as a result of that effect. With the seismic analysis, we can estimate how much the structure will deform, how much forces will be generated, and how much load would a structure have to take in order to respond properly during those types of events. It is also important because with that we can get many consequences, such as lateral loads applied by the earthquake, vibration loads, additional forces due to the P delta effect, and also we can get like a nonlinear behavior of the steel and the concrete of the structure. So, having an idea of what would happen, it is a way for us engineers to kind of prepare for those types of events and prevent things like this, which are basically collapsed bridges due to those type of forces. So we're gonna try to prevent this with this and go over the different types of analysis. So there are four main types of analysis, going from static to dynamic, and from linear or elastic to non-linear. Starting from the static one, we have the static elastic, which is the equivalent force method. It's a very simple way of analysis in which we apply usually lateral loads in order to simulate the effect of an earthquake. We also have, in the elastic range, we have a dynamic type of analysis, which is called the response spectrum. And then going into the nonlinear portion, we have the pushover analysis, which is an static nonlinear. It considers the nonlinearity of the properties of the materials of the bridge. And then we have the nonlinear dynamic analysis, which is a nonlinear, or will be a nonlinear time history analysis. We're gonna talk a little bit more about it later. Now, jumping into the static analysis. Static analysis is the type of analysis in which the seismic load is represented by a static load applied in the direction laterally to the structure. It is relatively simple and easy to apply and understand. You don't really need a rigorous calculation, and it's relatively fast. We've seen this type of analysis since we started engineering school, and it's, as you might know, relatively simple. The only or the major issues that it has, it doesn't take into consideration the dynamic response of the structure, and also the nonlinearity of the materials. So we don't get that full range of the steel and the concrete in during these types of events, and it doesn't really give us a detailed response to earthquake. It is a very simplified method of simulating a load or those type of loads. So sometimes it's used, sometimes not so much, depending on the zone of the or location of the bridge, but it is one of the types of analysis. Then we have eigenvalue analysis, which is basically the vibration shapes that the structure will take. And in order for us to apply it in the program, we first have to specify the structure mass, and then define the eigenvalue analysis control, and then going into the results. First, defining the structure mass. In MyDecibel, the mass can be defined in the following ways. We have the lumped mass and the consistent mass. Lumped mass, as you see, you have it lumped at the nodes, or you have them basically just at the nodes, and the consistent mass, you have them all over the structure. The lumped mass can be defined in the following ways: using the structure type, using nodal masses, and also using the function that is called loads to masses. In order for you to do that in the program, let's go over one of the models that I'll be working on today. In order for you to do this, you first have to define the masses. So we go into the structure and use the structure type function. Here, as I mentioned earlier, you can define whether you want to have lumped mass or consistent masses, and here you have an option of defining or converting the self-weight into masses. So this will be one way of doing it. Using the consider of the diagonal masses, you basically consider the mass at the center of the section if the section is offset, if it's defined. Just in case you have any offset of the section, you can also consider that. And then we have the consistent mass option, which can be applied as well in this particular portion. Here we define the convert self-weight into masses function, which basically what it does is it converts all the self-weight of the structure using the density of the materials into masses. Then we have an option in the program that is called nodal masses, which is this one. Just in case you have additional masses that you want to consider, like certain type of loads or something that the bridge is gonna be having on, so you can simulate it through nodal masses, which are this one, and you can define its direction and its magnitude using this dialog box here. Then you have the option that is called load to masses, which is this one right here. You can find it under the load tab, structure load and masses. And this one, what it does is basically it converts nodal, beam, floor loads and pressure loads that are applied to the bridge into masses. So if you have any load cases that have these loads and you want to convert them, let's say you want to convert 100% of the self weight, or one of these loads that is belongs to the self load case, you apply it. If you want to put like 25%, you add 0.25, just for your information, and then you click OK. That will be another way of defining the masses in the structure. Another thing about this eigenvalue analysis is that you have to define the eigenvalue analysis control. So in the program you have different types of analysis, such as the eigenvectors and Ritz vectors. For the eigenvectors you have two types, which is the subspace iteration and also a Langsos one. The subspace iteration is effectively used when performing eigenvalue analysis for finite element systems of large scales, which have large matrix systems. The Langsos is tridiagonal matrix and is used to perform eigenvalue analysis. Is effectively used for when performing eigenvalue analysis for lower modes. And if you have a complex model, then this analysis will be fast. These are the two types for the eigenvectors, and then we have the Ritz vectors. Unlike the natural eigenvalue modes, dependent Ritz vectors produce more reliable results in dynamic analysis with relatively fewer modes. The Ritz vectors are generated reflecting the spatial distribution or the characteristics of the dynamic loading. So here you can define the number of generations for each load case, and then from there the program, what it's gonna do is it's gonna take that information and generate each mode. In order for you to go to the eigenvalue analysis control, you go into the analysis tab and then you go into the eigenvalue. In this case, we're going to define for mode shapes. For this particular one, we're going to use eigenvectors and we're going to use Langsos. Here you define the number of frequencies or mode shapes that you want the structure to have, and then when we run the analysis, we're going to check its mode shapes and so on. Then for those of you who are doing construction stage analysis, we have an option to convert the final stage for the cable analysis to be used for determining cable stiffness for eigenvalue analysis, just in case you do any cable bridges and you want to perform the dynamic analysis of those cable bridges. Then you can use this function in order for it to be added, that stiffness, into the eigenvalue analysis. So in eigenvalue analysis, we can check the natural modes, the natural periods, the modal participation factors, the effective modal mass, and it must be preceded the dynamic analysis, such as modal time history or response spectrum analysis. So in order for you to perform time history or response spectrum, you have to perform the eigenvalue analysis. So let's go over and run the analysis for this bridge with that information already there. Let's take a look at it. And as this mentions, the response spectrum analysis uses the natural periods from the eigenvalue analysis in order to give you the response of the structure. Let's check the results. If you go into vibration mode shapes, you can see graphically the different mode shapes of the structure. Mode 3, for example, you can see them here. And also you can check the period, frequencies, natural period of the structure, even the mass participation as well. We go higher than the 90%. And here all that information can be obtained via the table for this one. So you can get them right on this table and check those frequencies and periods as well. Then going into the response spectrum analysis. In the response spectrum analysis is the dynamic analysis of the structure subjected to an earthquake excitation using the response spectrum. It is basically a plot of the peak or steady state response, displacement velocity or acceleration of a series of oscillators of varying natural frequencies that are forced into motion by the same base vibration or shock. The procedure of response spectrum analysis in the program is you first have to have the eigenvalue analysis defined in the program, and then you have the mode shapes. With the mode shapes, you obtain the frequency periods and the modal directional factors, and then from there you have to perform the response spectrum analysis. For the response spectrum, you first define a response spectrum function, and then you define the response spectrum load cases. And then you obtain the response spectrum results. So, first step, define the function. In the program, we have a database that you can use to define the response spectrum function. It's going back into this model, and let's open it up. If you go to the load tab, we have an entire dynamic analysis option where you can define the response spectrum, and also you can define the time history functions. If you want to define a response spectrum function, there are two ways of doing it in the program. A dialog box will pop up like this one, and you can either use the design spectrum and define as per the $RFD or the ASCE7 the side class and the peak ground acceleration. You can define them here depending on the location of your bridge, or another option in the program is using a response spectrum from an Excel like this one. If you have an Excel sheet, you can select and copy the response spectrum and simply paste it on this one, and that way you can generate the response spectrum. Or if you use the design spectrum, here you have the information of the RFD design spectrum. There are different types of spectral data. You have a normalized acceleration, which is the spectrum obtained by dividing the acceleration spectrum by the acceleration of gravity. You also have the acceleration spectrum, velocity spectrum, or displacement spectrum. You can select them here. Naturalized acceleration is the one that is coming up, that will come up by default. And then we have to define the response spectrum load cases. So the first thing you do is you define the excitation angle. Excitation angle is the direction in which you are going to apply the response spectrum function. Excitation angle is parallel to the XY plane in the program, and you reference the degree to the z-axis, which will be the vertical axis, using the right hand rule. The angle 0 is at the x-axis directly. So let me just show you here. After you define this response spectrum function, you go into the load cases, which is this one. So let's say you want to define the response spectrum in the x direction. You will need to define an excitation angle of 0, which will apply it directly on the z-axis, on the x-axis. Then you have different modal combination controls in the program, or modal combination types. We have the SRSS, which is the square root of the sum of the square, the complete quadratic combination, and also we have the absolute sum of the different responses, and then we have a linear sum. The complete quadratic combines the spectral results using structural damping and weight ratio of relative frequencies. The act of combination removes the sign of the results, thus leaving only magnitude for the final answer. You have the option of assigning or adding the positive and negative to the results, where you want to restore the signs deleted during the mode combination and specify the restoration method. You can define them here, the restoration method. We have the option of defining along the major mode direction, the absolute maximum value, and here you can select the mode shapes to be used in the modal combination as well. So let's go back to that in the program and define it here. You have this option which is called the modal combination control, and here you can define the modal combination type, whether you want to add or not the negative or positive results, and then you select the mode shapes. Usually it's gonna come up with all of them selected by default. Then we have interpolation of spectral data for finding the spectral curve for different damping ratios. We can use the following methods, which are the correction by damping ratio, or the interpolation of spectral data, which can be linear or logarithmic. You can define it here, whether or not you want to apply the damping method, and you define the method that you want to use, and here you can define the interpolation of the spectral data. For the damping method, you have the modal damping method, which is defined basically for defining the damping ratio for each mode, and the modal response will be calculated based on the user defined damping ratios. Then you have the mass and stiffness proportional, in which the damping coefficients are computed for mass proportional and damping and stiffness proportional damping. And then you have the strain energy proportion, which is damping ratios for each mode are automatically calculated using the damping ratios specified for element groups and boundary groups in group damping, which are used to formulate the damping matrix of the structure. So after we define response spectrum in the x direction, we here select the function that you want to use. Interpolation of the spectral data, we add it, and we have the direction and the scale. If you want to define it in the y direction, we're gonna have to use a 90-degree in order to make it perpendicular to the previous one, and then we add it. With that, we can run this analysis and see what the response of the structure will be due to the applied earthquake load. So here internally the program is calculating the response spectrum, and then we're gonna check those results. If you go to the results tab, in the program we can obtain different reaction forces, deformations, and so on. So let's check the force diagrams due to the response spectrum in the x and the y direction. In this case, for example, let's use keep inches, keep foot, and define or check the moment using the legend and using the fixed. We can check the moment due to the x response spectrum, and we can also check the y, which will be in this case MC, which is in this direction. Those are the moments generated due to the spectrum in each direction. You can also obtain the deform or displacement contour due to that particular load case. You can even deform it. You can deform it exaggerated using this function, and you can tell how much is deforming due to that particular load. You add that response spectrum into your load combinations, and then from there you can check the response of the structure due to the response spectrum analysis. Then in the program we have the pushover analysis, which is, as you might know, a static analysis that considers the nonlinearity of the structure. Um, and it basically what it does is you apply a lateral load, incremental lateral load that will generate certain force and deformation of the structure, and then from there you can obtain its behavior, which will be simulated during the earthquake. For the procedure of pushover analysis in MIDAS Civil, you first define the pushover global control, then you define the load cases. After that you define the hinge properties, which have the nonlinear portion of the structure, and you assign those hinges, and then you check the results. So the first thing is defining the pushover global control. If you want to perform the pushover analysis, you have to define this global control. Here you tell the program whether you want an initial load. In this case, you can perform the nonlinear static analysis for initial loading, and if you have any load cases that you want to use as your initial load for the pushover analysis, you can tell the program where or its location. If you want to reduce the stiffness for the skeleton curve, you can also do that here, where you have bilinear or trilinear skeleton curve. You can specify the stiffness reduction using the pushover global control. So let's go to the program and take a look at that particular one. In this case, we have a very simple pier. For the pushover analysis, we usually, or to make it more simple, we simplify the structure and only do the analysis at the piers. It's usually done at the piers for a bridge, and what we do is we simulate this behavior by applying the dead load of the structure and the live load as a nodal loading, and that way we have the initial condition of the bridge. With the initial condition of the bridge, then we apply some lateral loading that will simulate earthquakes, lateral such as X and Y. And in order for us to make it more simple, we apply those loads that will simulate the superstructure loading on the pier, and then we go into the analysis tab and define the analysis, or sorry, the pushover tab, and we define the pushover global control here. Using the pushover global control, you can tell the program whether you want to consider geometric nonlinearity, such as the large displacements. You can also perform it for the nonlinear static analysis, as I mentioned. You can tell the program which are the load cases that you want to consider as the initial loads, which are the ones that we applied. If you want to add any type of load with this factor, you can add it. For example, let's add a portion of the live load, 25% of the live load. You can also add it as well right here. After that, we go into the definition of the pushover analysis load cases. Pushover analysis load cases, we use the initial load in order for you to accumulate the reaction or displacement due to the initial loading to the pushover analysis, which in this case will be the dead load. If you want to use the initial load, you can define it here. Also, you have the increment steps, which is basically the number of steps that you want to use for the pushover analysis. As I mentioned earlier, pushover is an application of a lateral load, usually in increments. So here you can define the amount of increments that you want to have, and then we have an option that is called the increment method. Increment method is basically the way that you want the program to increment um, or to perform the pushover analysis. You have an option called the load control and another one that is called displacement control. So you can do the analysis either by increasing the force or by increasing the displacement of a particular node, which will be in this case a master node. You can define the direction in which you are applying and the maximum displacement. So using this point 3 for example and the 30 steps, the program will be increasing the displacement in the x direction. The program will be increasing it laterally, those zero point 0.3 meters into 30 steps. So basically divide the 0.3 into 30 and then you get the force or the displacement on each particular step. Then you have a load pattern. You can select either you want to use mode shape, modal, or an uniform acceleration. In this case, let's go into the load cases, and let's say that you want to perform the mode X. You tell the program the number of steps, you tell the program the node that you're gonna use. In this case is node 34, which will be this node right here, and the direction in which we're applying the load. You have the static load cases, uniform acceleration, normalized mode shapes, and the mode shape. We have different defined here. As you see, if it's the x-axis, we define everything on the x-axis. That is also an important thing to do. Let's say you want to check the y direction. Let's define the number of steps. Here we can use load control or displacement control. Usually it's done using the displacement control so that you can just move your structure and see what happens to it as you move it. And then we can pick the node directly here and define the direction in which we want the node to move. After that, in the program we have to define the hinges, or which are going to have the nonlinear portion of the bridge. So if you want to define, or if you want to consider the nonlinear portion, which is one of the reasons you perform in pushover analysis, you have to define the properties of the hinges that you want to assign into the elements. You can define different types of interaction, moment rotation, moment curvature, or moment curvature distributed or lumped, and you can define the components that you want to select for the column for the interaction, XYZ, forces or moments in each direction. So let's take a look at the hinge properties. We can use the define hinge properties. As you can see here, there's an entire pushover tab for performing the pushover analysis. So in this case we have the PMM, a type of pushover that we have defined. You can define the material that you're using, the type of element that you're using, and then you can define the type of rotation and interaction that you want to use. In this case we use FEMA, and we define the yield surface properties for this particular element. Internally, the program can automatically calculate these properties, or the user can input them for the interaction curves. After that, we can go, okay, we have different types of a skeleton curve such as the bilinear type or the trilinear type. It's up to you which one you want to use. In this case we used FEMA, and after you define the properties you have to basically assign those properties into the particular hinges. So after we define it, we can tell the program or use the function for assigning those particular hinge properties, and we can select the elements that are gonna have those properties, such as this right here. You can use them on a particular part. For example, here we have them on different elements. Let's just delete them and reapply them so you can see the procedure. So let's click on assign hinge properties. We have it as beam column, and we use the hinge that we just defined. If you don't have any, you can click here and this dialog box will pop up so that you can define your own hinge properties, and we basically apply it, and the program is gonna generate these these circles divided into 6 parts. So after this we have them assigned already, and we can go into the perform analysis. You can select which modes or you want to perform the analysis for, or you can perform for everything. Let's just, for the sake of time, let's do X static and Y acceleration so that we can see how this behaves, how the bridge will behave for each one of them. Okay, 6 seconds to run, and let's see the deformations due to this pushover analysis. So here, as I mentioned, or as you saw, we had 60 steps defined. So let's check mode 1 for the first step, and let's check on the value legend portion. So we have, you know, nothing much going on in the x-axis because of the step 1, step 4 as well, step 16. Then we're having yielding, a little bit of yielding, let's say like 20%. We go up and we can keep increasing, and we have the different yieldings for performance. Let's say for FEMA, for example, which is the one that we defined, we can obtain the different yieldings, and we have the definition of, as per FEMA, you know, collapse, low occupancy, or immediate occupancy, I'm sorry, or, you know, as the FEMA defines the different classifications. Since we selected FEMA, we can see graphically as well what level after the earthquake we will obtain in this particular structure. So this one went very well, no collapse. If you define the static one, we have a little higher risk, and this is in the Y direction. These are the hinge statuses as per FEMA, and for each one you can tell the hinge status for each one of the steps. You can also obtain the pushover curve for each mode. Basically, for each one of the modes you can see up to how much the bridge will handle, how much deformation it will handle, and you can even obtain a performance point if you select the FEMA. If you select FEMA, for example, This is the base and shear displacement. You can get shear coefficient versus the displacement, shear coefficient versus drift. If you have any load factors, you can also apply them. And then if you want to obtain the performance point, here the program tells you that it failed because you don't have any design spectrum. Let's say we use the same spectrum that we had before, and we can define the design spectrum for each one of these dampings ratios. So let's say for 25. If you want to define, you can see here for each one of the damping ratios you can obtain the performance point for each one of them. You can generate a graph out of this capacity, or you can generate it white, black, you can save it, you can get it as a text. It's up to you how you want to do it. Same thing for the static or the y direction as well. And the good thing about this is that you can get the performance point. You can see how your structure is behaving because of that demand that you're applying. Demand is based on the location of the structure, soil properties, and so on, and its capacity is based on its materials and how its properties are assigned to or defined in the model. You can also check the results for the hinges. So as per steps, you can see what the first yield for each step is, and you know, a more detailed option or way of getting the yielding on the pier due to a particular displacement or due to an earthquake, basically. Then we have the time history analysis. For the time history analysis, we have two types. We have the boundary nonlinear time history analysis, and we also have the inelastic time history analysis. Boundary nonlinear is used to analyze structures with nonlinear support conditions, such as base isolators or viscous dampers in seismic events. Those support conditions are what is called control systems for seismic. And we also have the inelastic time history analysis, which is for the dynamic analysis that considers the material nonlinearity. Time history analysis in this case is basically the nonlinear model of the structure combined with the seismic input, which is basically a ground motion or an acceleration, as you can see here. For time history analysis, we have the linear case, and we also have a nonlinear case, which can be you know, changing the stiffness of the section, and also for if you have any systems, you can also obtain that nonlinearity in the structure. For the time history analysis, this is the procedure. This is a kind of complex analysis, and it's used in very high seismic zones, or depending on the type of structures for complex bridges it is used. And the first thing that you do is you define the properties of the nonlinear links. The links are used to simulate those control systems, such as dampers or isolators. Then you have the input for the nonlinear links. Those inputs, we will see how to define them. Then you have the load cases, similar to the load cases that we define in the response spectrum. And then we have the time history forcing functions, which is basically the acceleration or accelerogram that we're gonna add to the model. Ground acceleration direction basically of the where we're applying the load, perform the analysis, and then we check on the results. So first we define the general link properties. These properties are usually defined, let's use this model for it. So if you go into the load boundary tab, we have an option for defining general links. General links are links that we use to simulate the behavior of those control systems. If we go to the general link properties, in the program we have different types of properties. We have the force type, which are the control system elements, such as the viscoelastic dampers, hook, gap, hysteretic systems. We also have lead rubber bearing isolators. We have friction pendulum system and triple friction pendulum available. We also have the element type, which are springs, and we also have newly implemented control devices, such as the isolators, hysteretic isolators, and the dampers as well. For those dampers, you can manually define from our database the different types or properties of those particular hysteretic system function. Let's check on these isolators, for example. You can tell the program or generate a database for the different types of isolators that we have available, and you can define their properties and so on. After that, as I mentioned, we have different types: lead rubber bearing, friction pendulum, and you basically tell the program what their properties are, their linear and nonlinear properties, such as the stiffness and the nonlinear portion as well. You can define it here: linear, nonlinear in each direction. Depending on which type of device you have different types of options for defining its nonlinear properties. This is a triple friction pendulum. You can see here how triple pendulum will behave, and the properties that you should assign to it. And you can define the linear and nonlinear properties for each one of the different devices that we have. After you define that, you have to tell the program where those elements are. Those elements are assigned to nodes, and you basically tell the program which two nodes are the ones that are gonna take those elements. For example, if I want to assign those elements after I define them, I go into the general link tab. I have two types. I have the LRBA and LRBP, one for abutment, one for the pier. And here I can tell the program which two nodes are going to be assigned to it, and the program will show it like this. You can copy it X, Y, and Z direction if you have the same location, for example. You can do that as well in here, and the program will basically copy it. If you want to check graphically where they are, you can tell with their number the locations. We have defined in this bridge the location of each one of the LRB isolators, which are the lead rubber bearing isolators. And then you go into the time history load cases. Here you have the option of defining the analysis type, where you're doing linear or nonlinear analysis. As you can see here, you have the analysis method. You have three types: modal, direct integration, and the static. And then you have the time history type, which can be transient or periodic. Transient time history is carried out on the basis of loading a time load function only once. This is very common for simulating the earthquake loads, and the periodic usually is used to represent vibrations of machines, and a function that it can which has a period identical to the end time, and is usually used for the machine vibrations. It's like a periodic, like it will repeat the loading as a time function. Then you have the order in sequential loading. You can use that to select a time history analysis condition previously defined, which precedes the time history analysis condition currently being defined. This function is used usually to represent the load conditions, such as the dead load, that will precede the actual earthquake load that we'll be applying into the model. Damping method, you have three different types: modal, element mass and stiffness proportional, and strain energy proportional. For element mass stiffness proportional, the relevant has to be provided in, and then we define the function. So let's go into the load cases and define each one of the load cases. So we're going to the load tab, dynamic loads, and here you define this, all the time history function that are already there. First thing we do, we have an earthquake, we have a nonlinear dead load. This nonlinear dead load, what it does is basically take the dead load and apply as a first stage, or as a initial condition, basically. So we have two types of load. We have the load cases: the dead load, which is this one, defined as a nonlinear modal transient one, and then we have the earthquake. With the earthquake, we use the order in sequential loading, meaning that the earthquake load case is subsequent to the load cases using the dead load function, which is this one, the static one. If you see here, the load function is a static dead load, which will be simulated like this one with the self weight. So just keep in mind that in order for you to take into account the self weight of the structure, you have to define a dead load case. And then for the earthquake, nonlinear modal, time, end time, the increments, you can define them here. The damping ratios, and then we define the time history forcing function. In the program, we have different types of functions. You go into the time history function. The first one that we use is the ramp. This ramp is gonna simulate the change on the dead load. This is like a first stage one, and then we have different types in the program. If you go to earthquake, we have a database with different types of earthquakes around the world, or you can import it as I did, copy and pasting from the Excel sheet. It's up to you. We have two types of functions right here, and then from there you have to define the ground acceleration, which is basically in which direction the forces or the earthquake will be applied. So here is very similar to response spectrum 1. You can define the rotational angle about the global coordinate system z-axis, defining the direction of the component for the ground acceleration, which is this one. Here's the sign convention. and basically you go selecting the load case, and then you define the function scale factor in which direction you're applying it. So we go into the ground acceleration, and we can take the earthquake and define it in the x-axis with a scale factor of 1, which basically will apply the earthquake on this axis, which will be the x1. We close it. In the program there's also a function that is called dynamic nodal load. The user can do the time history analysis moving load using this feature, which is basically a change of a nodal load on the structure if you want to simulate the moving load using the dynamic time history analysis. For this case, let's run this analysis and go over the time varying static load. This function is used to reflect the effects of the self-weight in the time history analysis due to the seismic loads. You first define the self-weight using the time forcing functions, then you assign the time history to this load case for the self-weight. You define a time history load case for the seismic load, selecting that self-weight load, and then you use the subsequent load case, which is the ones that we did for this earthquake. And in the program you also have a very particular function that is called multiple support excitation, which is in a structure with multiple supports, different time history forcing functions are, in terms of ground acceleration, can be applied to different supports at varying time. So you can tell the program the arrival time of each one of the functions. This is used in very large bridges where we have, the earthquake doesn't get there to all their supports at the same time. So you have this option for defining that part. And let's check here what the forces we obtain on the isolators, and see what happens to it. So program took 20 seconds to run the time history analysis using those functions, and then from there what we can do is we have particular results that we can obtain in the time history analysis, and those are here in the time history results. So in the program, if you want to, for example, obtain the forces, displacement, acceleration, or velocity for a particular step or a particular function, you can step on top of each of the load cases and you can obtain the displacement, velocity. You can add a legend to it as well. If you want to obtain the acceleration during the earthquake with the values, you can get the values here as well. You can do that. If you want to obtain the forces for the beams, for example, you can get the forces at the beams for each load case. You can even run a video and get the graphical result of the time history force. You can also check the forces on the links. Or the diagrams, for example, in here you can obtain a moment diagram, solid with no deformation, and you can see what's happening to the structure in each load case. Another thing that we have for those seismic devices, control devices, is the graphs that we can obtain in the program. If you go into the time history results, time history graph, we can define different types of functions in the program. For example, if we want to obtain the shear force and of a particular link, we can define the link number, which will be 3, which is this one, and we get the deformation with each component. This will give us the deformation of this particular element. Or if you want to check the shear, you can get the Fy with this particular load case, and in the program from there you can obtain a graph. If you go to results, time history graph, and from here, let's say you want to check the shear. If you check the shear with the displacement in the horizontal axis, let's add the shear in the vertical, and the horizontal one will be displacement. You can tell the name of the and the decimal point, and the program will generate a graph like this one that will show you the behavior of this particular isolator during that earthquake. You can do the same to obtain the displacement of a particular element, such as, let's say, displacement in the horizontal function, and let's say here displacement versus time, and here you can get the displacement of the isolator, which is a NL3. You give the name to the bridge, and you can from there obtain the displacements on this particular element. If you want to obtain the displacement at the top of the pier, you add a function that is called displacement. You select the node that you want to check, and you tell the program that you want to check the displacement of that particular node. Then from there you can get a graph. You go to the my.civil, you get a graph of the displacement of the pier. Let's delete this one and add the pier tab in time. This is the displacement of the pier, the top of the pier versus time. You can see from here how much that part of the structure is moving during the earthquake. Those graphs can be, you can zoom in, you can zoom out, you can export to Excel, you can generate a text, you can save it as an image, and those, for the detailed report, you can also use them for your analysis. Alright, thank you so much to all of you for your attention. I hope you enjoyed the webinar. If you have any questions, please let us know, and we'll be happy to help. Thank you very much, and have a good evening.